Imagine we have a robot and it's standing in the middle of the road because it doesn't know that cars are dangerous. Let's set our x-axis to be parallel to the road, and let's say the robot is at the origin, so the place where x equals 0. The robot is programmed to walk off the road at exactly t equals 4 seconds. Now say there's a car approaching, and at t equals 0, the car and the robot are separated by 140 meters. Since the robot is at 0 meters, that means the car must be at minus 140 meters. And let's say we know the velocity of the car at any given time point t, which is given by this equation. Just like the equations from the previous videos, this one also has units in it. The m and the s that appear on the right hand side aren't variables, they're units, meters and seconds. These are there so that when you plug in a value for t, which has units of seconds, you'll get out to a final answer that has units of meters over seconds. The graph of the velocity looks like this. I want to know if the car hits the robot. We know that at t equals 0 seconds, they're separated by 140 meters, and the robot walks off the road at 4 seconds. So I need to know between t equals 0 and t equals 4, how far does the car travel? But we only have the velocity as a function of time, not the displacement as a function of time. So this seems like a pretty tricky problem. In the video on instantaneous velocity, we saw that if we knew the displacement, x of t, we could get the velocity by differentiating x. Now we have to figure out the inverse of this problem. We know v, and we want to find out x. Before we tackle this problem, let's look at a more simple example. Imagine the car had a constant velocity of 10 meters per second. In that case, it would be easy to calculate the distance traveled in 4 seconds. The car has traveled 10 meters every second, and it went for 4 seconds, so you just multiply 10 by 4, and you get to an answer of 40 meters. By the way, that result just follows from our equation for the average velocity. You just multiply both sides by delta t, and you get your answer for delta x. Now here's the really cool part. If you look at the graph again, 10 times 4 is just the area under the graph between t equals 0 and t equals 4. This rectangle has a height of 10 and a width of 4, so the area is just 10 times 4, which was the distance that the car traveled. By the way, just keep in mind that this graph you're seeing has its v-axis scaled down just so that it would fit on the screen. Okay, let's go back to our original problem. The distance traveled between 0 seconds and 4 seconds is just going to be the area under this curve. Now at this point, you might be a bit skeptical. You might be saying that I only proved that the area is the distance traveled for the constant velocity case. But now we have this crazy velocity graph. So does the area still give us the distance traveled? The answer is yes. I'm going to try to convince you of that. Let's approximate the car's velocity graph with this velocity graph. So in this one, we have constant velocities, but every second the constant velocity changes to a different value. Now I know the car didn't really have this velocity graph. It's not perfect, but it's pretty close. You can see how close the velocities are at any given point in time. To get the distance traveled by this approximate velocity graph, we can just find the distance traveled in the first second. That would just be the area under this constant velocity. Then we can find the distance traveled in the second interval, which would be the area under that interval. And we do that for the next 2 intervals. Then we just add that together. So we take the total area that you see here, and that's the distance traveled for this approximate velocity time graph. Let's make the approximation even better. This time we're going to be using half-second intervals. Now to get the distance traveled by this approximation, we just look at the area under each interval, which is the distance traveled in that interval, and we sum it all together. So we take the total area here to be the distance that the car traveled if it had that approximate velocity. We can get an even better approximation by using quarter-second intervals, and the distance traveled is going to be the area under that graph. You can see that as the time steps get smaller, the approximate velocity graph gets closer and closer to our real velocity graph. And you can also see that the area under the approximate velocity graph is getting closer and closer to the area under our real velocity graph. So hopefully now you believe me that the area under any velocity graph is the distance traveled. Fortunately, to get the area, we don't have to use smaller and smaller approximations every time like we just did. Thanks to the guy who invented calculus, we can get the area under the graph by just taking the integral. That's kind of how the integral of a function is defined. It's just the area under that function. So for our function vx, the area under it is the integral of vx from t1 to t2. And this area is the distance traveled. So we have the following equation. The distance traveled equals the integral of vx from t1 to t2. For those of you who actually remember how to use integrals, let's go ahead and plug our function in and integrate it. Usually it's a good idea to keep the units around, but I'm going to get rid of them just because I don't want to have to keep writing them over and over again. So sorry if you think I'm being sloppy. The next step here is to use the sum rule of integration, which tells us we can integrate each term separately. I'm going to pull out the constant factors, and then I'm going to integrate. I plug in the limits, and I get to the answer of 57.1 meters. That's great news for our robot. The car was 140 meters away, and after 4 seconds, it only travels 57 meters. So that means the robot's going to have plenty of time to get off the road before the car passes.